everyone. Today I want to share with you a critical challenge facing our chemical and pharmaceutical industries, and more importantly, a proven solution that is transforming how we manufacture medicines and chemicals sustainably. The topic is biotransformations in green solvents. This is a field that sits at the intersection of environmental responsibility and practical chemistry innovation. Over the next minutes, we will explore why this matters, the science behind it, and we will present some real-world examples showing it is not just possible but commercially viable today. So let's start with the context. Why do we care about sustainability in chemical processes? The answer is threefold. First, the role of sustainability. We must minimize environmental harm, conserve resources, and ensure our industries remain viable long term. Sustainable practices reduce three things: hazardous waste, emissions, and our dependence on non-renewable materials. This promotes genuinely greener chemistry. But there is a problem. What are the challenges in conventional synthesis? Traditional chemical processes rely heavily on toxic solvents and reagents that generate harmful emissions and hazardous waste. They depend on fossil-derived chemicals that deplete resources and create massive carbon footprints. And over time, these persistent toxic substances accumulate in ecosystems and organisms, creating long-term health risks. The urgent question that becomes, what are the alternatives? We need greener solutions, and they exist. Three main pathways are emerging: bio-based solvents derived from renewable biomass, enzymatic catalysis that harnesses nature's own catalytic efficiency, and renewable feedstock, replacing petroleum sources. This is where we are headed in this presentation. So what is biocatalysis? It is the use of natural catalysts, primarily enzymes or whole cells containing enzymes, to accelerate chemical reactions under environmentally benign conditions. The concept is very elegant. You just take your substrate, you add a biocatalyst, an enzyme, place it in an appropriate reaction medium, and it will produce your desired products with remarkable efficiency. The core advantages of this approach are quite powerful. First of all, high selectivity. Enzymes are exquisitely selective. They exhibit chemo, regio, and enantioselectivity simultaneously. So this means that you can get your desired product with minimal unwanted byproducts. This is crucial for complex pharmaceutical synthesis where you need only one specific stereoisomer. Second one, mild reaction conditions. Unlike harsh chemical catalysis requiring high temperature and pressure, enzymatic reactions typically occur at or near room temperatures in aqueous solution. This drastically reduces energy consumption and safety hazards. And finally, sustainability and low environmental impact. Enzymes are biodegradable, they are derived from renewable resources, and dramatically reduce or eliminate toxic chemical use. The waste profile is fundamentally different from conventional chemistry, and there are some other benefits too. Reduce safety risk, cost effectiveness due to lower energy and purification requirements, and continuous potential for enzyme engineering improvement. The promise is clear, but there is a catch. We need to talk about solvents. Here's the real issue with biocatalysis. Enzymes work perfectly well in aqueous media, which is genuinely green, but there is a systemic problem across the entire synthesis workflow: solvents. In a biocatalytic transformation, the reaction medium, that is the solvent, is where your substrates must dissolve, where your enzyme operates, and where products were formed. And it is waste ultimately. But the larger problem emerges in workup and purification. You need multiple rounds of solvent extraction, washing, and crystallization. This multiplies solvent consumption dramatically. The critical insight is that enzymes can work in aqueous water-based system, which is inherently more sustainable. But by shifting towards some other green solvents and other aqueous conditions, you can achieve multiple benefits simultaneously: reduce solvent waste, improve sustainability metrics, and cleaner chemical process. But we can go further. What if we could combine enzymatic selectivity with these truly sustainable bio-based solvent systems? That's the vision driving this field. The scenario is very serious, especially in pharmaceutical industry. Let me illustrate why this matters at a concrete level. 1 kilogram of active pharmaceutical ingredient requires between 168 to 308 kilograms of total material. This includes solvents, reagents, everything. So the median is roughly 200 kilograms of material per kilogram of drug produced. And here's the critical statistics. Solvents account for 80 to 90% of the total mass used in the reactions, and they represent between 80 to 85% of all waste produced. So when you manufacture 1 kilogram of medicine, approximately 200 kilograms of solvents generate waste. This is serious, but wait for the scale. In 2023, global pharmaceutical production exceeded 680,000 metric tons of active pharmaceutical ingredients, supporting more than 4,500 of different drugs. If we apply our calculation, that means 680,000 metric tons multiplied by 200 kilograms of solvent per kilogram of API equals to 1.23 billions of kilograms of solvent waste annually. Put differently, 1.23 billion liters of solvent per year only coming from the pharmaceutical industry. To visualize this scale, considering that an Olympic swimming pool holds approximately 3.25 million liters, the solvent waste equals roughly 380,000 Olympic pools completely full, filled just from pharmaceutical manufacturing in a single year. Considering we are talking about water, this is outstanding. This staggering volume underscores the absolute urgency of transitioning pharmaceutical manufacturing to genuinely green solvents, biocatalytic processes, and sustainable alternatives, not just for regulatory compliance, but also for planetary sustainability. Here we've got a conceptual paradox. 1.23 billion liters of water-based solvent would be a significant environmental issue. But think about 1.23 billion liters of toxic petroleum-derived solvents. This is an existential crisis. We universally accept that water is a green solvent. So the question sharpens. What criteria truly define a green solvent? What is a green solvent? A green solvent must meet several criteria. A green solvent must come from a renewable or abundant feedstocks. It must be biodegradable and non-persistent in the environment. It must have minimal toxicity to humans and ecosystems. It must produce low VOC emissions, thus reducing volatile organic compound releases. Should be recyclable and reusable, supporting circular processes. It must align then with green chemistry philosophy under a holistic sustainability point of view. Is water a green solvent? Yes, water checks all these boxes. Water is a green solvent. It meets all 6 outlined criteria. But is water the greenest solvent? Is water the greenest solvent? That's more nuanced. While water is undeniable green, it is not universally applicable. Many pharmaceutical APIs are highly lipophilic, so they won't dissolve in water effectively. So the practical truth is that the ideal green solvent would be no solvent at all. That is working under truly solvent-free synthesis, but that's a theoretical idea that rarely works in practice. Why can't we just eliminate solvents entirely? Because of limited solubility and miscibility problems. In fact, reactant won't dissolve or mix without a solvent. Poor reaction control. Without a solvent medium, you can lose control over temperature, mixing efficiency, or reaction kinetics. You can have also heat dissipation problems. Without a thermal buffer, reaction can dangerously overheat. You will always need specialized equipment. Truly solvent-free processes require ball mills, microwave reactors, etc. Specialized apparatus that may not suit all transformation. You can have also catalyst compatibility issues. Many catalysts, including many enzymes, do require solvents environments to function. So the unavoidable conclusion is that solvents are needed. That's for sure. While solvent-free synthesis is theoretically ideal, it's chemically impractical and sometimes impossible for complex organic synthesis. This reinforces the urgent need to develop genuinely green bio-based solvents rather than eliminate solvents entirely. So the solution isn't no solvent. The solution is the most sustainable alternative when solvents are necessary. And in pharmaceutical manufacturing, solvents are nearly always necessary. There are different types of green solvents. Water for sure, supercritical carbon dioxide, ionic liquids, deep eutectic solvents, bio-based solvents, fluoro solvents, polymeric solvents, and some other renewable solvent derivatives. But this brings us to a pivotal question. Can enzyme work in media different from water? The answer fundamentally changed the field, and the story around this is really fascinating. Starting in the mid-80s, scientists discovered something remarkable. Some enzymes could function perfectly well in pure organic solvents. Not talking about aqueous solution, but genuinely organic media. This breakthrough is attributed to Alexander Klibanov at MIT, who published foundational work showing enzymatic catalysis in organic media. His 1996 book, Enzymatic Catalysis in Organic Media, became the field's cornerstone. By the turn of the century, non-aqueous enzymology was recognized as mainstream field and multiple textbooks appeared. The crucial insight that enzymes are inherently green catalysts, but traditional organic solvents are toxic and non-eco-friendly. So the opportunity is to combine enzymatic biocatalysis with green and sustainable solvents. This will create a winning strategy: enzymatic selectivity, green approach, plus renewable safe solvent media, green approach. This equals to true green chemistry. So what are bio-based solvents? Are those produced from renewable biological sources, plants, agricultural waste, forestry residues, biomass, that function as direct alternatives to traditional petrochemical derived toxic solvents. They've got different advantages which are compelling, coming from its renewable origin, the low toxicity and high biodegradability, the reduced VOC and greenhouse emissions, its functional efficiency, and the green standards compliance. But there are variations in how we achieve this. Let me show you two important approaches. Some bio-based solvents are drop-in replacements. They are chemically identical to conventional petrochemical solvents. As they are structurally identical, you can seamlessly replace them in existing industrial processes without modifying any equipment or procedures. They maintain equivalent performance, efficacy, and compatibility while offering significant environmental advantages through a lower carbon footprint. Think of these bio-based drop-in replacement solvents: bioacetone, bioethanol, bioglycerol, etc. Think of this as same chemistry, greener origin. Some other bio-based solvents are alternative replacement. They are not identical but functionally equivalent or superior. We are talking about solvents such as 2-methyl-THF, dimethyl isosorbide, gamma-valerolactone, ethyl lactate, styrene, or dihydropynen. This practical table shows some key examples of bio-based alternative replacement. You can just replace quite toxic NMP or DMF by using styrene, gamma-valerolactone, or DMI. You can use 2-methyl-THF, bio-based from renewable sources, to replace toxic THF coming from petrol. You can use bio-based ethyl lactate for substitution of ethyl acetate or acetone, which are volatile. Or you can use, for instance, dihydropynen, bio-base obtained for turpentine, to replace quite toxic hexane, toluene, or DCM. How do we obtain these bio-based solvents? The answer lies in lignocellulosic biomass valorization. In fact, wood, agricultural waste, food residues, and forest biomass contains three major components, which are cellulose, hemicellulose, and lignin. And through biorefinery processing, which is deconstruction and or fermentation, we can generate these C5, C6 sugars and lignin monomers and macromolecules with aromatic precursors. From these sugar platforms, we synthesize different platform molecules, represented in pink, which ultimately can be converted into bio-based solvents, such as ethyl lactate, gamma valerolactone, styrene, 2-methyl-THF, etc. So the vision is that these lignocellulosic waste streams are converted into a circular bioeconomy, generating value-added bioproducts, including these solvents, also polymers and also fine chemicals, thus maximizing waste valorization from single biomass feedstocks. Over the past 15 years, leading international researchers have published comprehensive peer-reviewed reviews demonstrating biocatalysis in green solvents. This publication establishing that combining enzymes with green bio-based solvent is not experimental, it's proven, scalable, and ready for industrial adoption today. This isn't theoretical speculation, it is the peer-reviewed scientific foundation supporting the field. This is the evidence base for transitioning your processes now, if you are in pharmaceutical or fine chemical manufacturing. Let me make this concrete with a landmark example, 2-methyl-THF. This is a bio-based green solvent synthesized from renewable biomass, cellulose and glucose. Importantly, it can be degraded through solar light and air exposure, closing the renewable loop. In 2009, Simeo and co-workers published a landmark study in green chemistry demonstrating the regioselective acylation of nucleosides using immobilized lipase B from Candida antarctica into methyl-THF. This results in a pharmaceutical-grade selectivity and excellent yields while eliminating toxic solving waste. This was not theoretical. This was a concrete lab-scale example proving that green bio-based solvents work perfectly well for complex biocatalytic transformation requiring exquisite selectivity. Here you can see some peer-reviewed evidence and concrete pharmaceutical example documenting the use of 2-methyl-THF as a very useful biomass-derived solvent with broad organic chemistry application. Now let's move to a real pharmaceutical example, the synthesis of ozanimod, marketed as Zeposia, a drug for relapsing multiple sclerosis. Ozanimod is a sphingosine 1-phosphate receptor agonist. It is an immunomodulatory drug that requires a single enantiomer amine precursors for its final steps. The synthesis uses 2-methyl-THF as the reaction medium combined with an enzymatic transformation catalyzed by an immobilized lipase. The result is a 99% enantiomeric excess with an overall yield of 20% through multiple step by chemoenzymatic cascade. So this validates that complex pharmaceutical APIs can be manufactured using this green biosolvent instead of any other toxic alternative. This is a real industrial production, it's not a laboratory curiosity. Here we've got another sophisticated example, converting biomass-derived hydroxymethyl furfuryl HMF, a platform chemical derived from renewable sugars, into high-value bio-based molecules. Traditionally, reducing HMF using lithium aluminum hydride generates massive waste, is prohibitively expensive, and it's unscalable. So the green alternative is to make a chemical reduction using non-noble metal nanoparticles into methyl-THF, immediately followed by enzymatic esterification with novozymes 4,3,5 lipase to produce PHMF dihexanoate. This is a bio-based plasticizer replacing petroleum-derived phthalates. So the result is a 91% total yield under 96% selectivity in a process in an 11-hour batch reaction at very mild reaction conditions. So this demonstrates that 2-methyl-THF is an enabling solvent for seamless integration of chemistry and biocatalysis. This is the vision, cascading reaction using multiple catalytic approaches in a single green solvent medium. Beyond bio-based solvents, another important class emerged: room temperature ionic liquids, RTILs. These are molten salts composed of organic cations, imidazolium, pyridinium, pyrrolidinium, phosphonium, paired with diverse anions such as hexafluorophosphate, tetafluoroborate, etc. The result is a colorless, low viscosity, easily manipulable liquid materials. These ionic liquids present remarkable properties. They've got negligible vapor pressure. They are completely non-volatile. They are non-flammable. They've got exceptional thermal, chemical, and electrochemical stability. They remain liquid over wide temperature ranges. They dissolve diverse organic and inorganic compounds, and they possess tunable properties for a specific application. The first documented biocatalysis in ionic liquids appeared in year 2000, very recently in scientific terms, by two landmark studies, one of them demonstrating thermolyzing a protease catalyzing complex peptide synthesis in room temperature ionic liquid with 5% of water, and the other one using lipase, immobilized lipase CalB for fatty acid amidation in room temperature ionic liquids. This first generation result proved that these solvents could enable enzymes to function while maintaining exceptional selectivity. This is a major breakthrough for demanding synthetic transformations. Here you can see some key reviews which have documented room temperature ionic liquids success not only in biocatalysis but also in metal, photo, and electrocatalysis. Let me show you now a hot combination: the use of room temperature ionic liquids and thermophilic enzymes, organisms naturally adapted to extreme temperature. A striking example is the use of BTL2 lipase from thermophilic Bacillus thermocatennulatus working at 120 degrees Celsius in room temperature ionic liquids, achieving excellent kinetic resolution of mandelic acid derivatives with greater than 99% enantiomeric excess. So that's enzymes working at temperature where some other solvents will vaporize. This demonstrated room temperature ionic liquids enable extreme temperature biocatalysis and locking transformation impossible in any other solvent medium. Now we arrive at what may be the most promising platform, deep eutectic solvents, DSSs. What are they? They are a mixture of two or more components, hydrogen bond donor and hydrogen bond acceptor, that interacts strongly through hydrogen bonding. This interaction causes the mixture melting point to drop far below that of the individual components, therefore creating a liquid at relatively low temperatures. They have many remarkable advantages: biodegradability, low toxicity, they're renewable sourcings, very low volatile organic compounds, they are not flammable, they are safe, they are customizable and versatile, they are recyclable and reusable, they produce a lower life cycle environmental impact, and especially the cost effective and scalability and the regulatory compliance. So DSSs represent the convergence of sustainability, performance, and practical feasibility. There are 5 recognized types of DSSs. Type 1, made by quaternary ammonium salt plus a metal chloride. Type 2 is a quaternary ammonium salt plus a hydrated metal chloride. Type 3, probably the most commonly used, quaternary ammonium salt plus molecular hydrogen bond donor. Type 4, made by a metal chloride hydrate plus a hydrogen bond acceptor. And finally, type 5, the most recently this reported, which are hydrophobic DSSs, made by non-ionic molecules only. Type 3 DSSs are formed by pairing quaternary ammonium salts such as choline chloride, betaine, etc., acting as hydrogen bond acceptors with molecular hydrogen bond donors like urea, glycerol, etc. There are some natural alternatives known as NADSSs, which include lactic acid, glucose, fructose, and sorbitol. Finally, type 5 DSSs, the most recently reported, they use hydrophobic components, only non-ionic molecules as both HBAs and HBDs, enabling the hydrophobic DSSs for specialized applications. This compositional diversity means DSSs can be tailor-made for virtually any biotransformation by selecting appropriate HBA-HBD combinations from renewable, GRAS-approved biodegradable sources. Based on the sarcastic film from Woody Allen in 1972, Abranches and Coutinho made puns in their recent comprehensive review. Everything you wanted to know about deep-protected solvents but were afraid to be told. This landmark publication covers all aspects of DSS's chemistry, biology, application, and environmental impact. That is, this is the definitive reference for anyone seeking complete DSS knowledge. This humorous visual metaphor emphasizes that, despite DSSs being intensively researched since 2003, many crucial questions and practical applications still remain underexplored. But right now, DS science is mature enough, well documented, and ready for widespread industrial application. The first documented example of biocatalysis in deep-protected solvents appears in 2008 through Gorkes, Schrenk, and Kaslowska's groundbreaking work published in Chemical Communication. They demonstrated lipase-catalyzed ester and amide formation using choline chloride, glycerol, and choline chloride urea deep-protected solvents, proving that enzymes work efficiently in this media. Since this landmark publication, an explosion of peer-reviewed research has documented DSSS-based biocatalysis across diverse applications. So this means that DSSS-based catalyzed biotransformation are scientifically validated, industrially relevant, and environmentally proven. The versatility of DSS-based catalyzed biocatalysis is shown across 6 major reaction types, as recently reviewed by Sang and Kara. We've got hydrolysis, aldol addition condensations, oxidations, reductions, aminations, cascades. So these real examples prove that DSSs can enable industrial-scale biocatalysis across all major synthetic transformations. Before our final summary, let me recap 6 key takeaways. First, the challenge. 1.23 billion liters of solvents used annually in pharmaceutical API production, with 80 to 90% becoming hazardous waste. This is unsustainable. Second, solution. The combination of enzymes with nature's exquisitely selective catalysts with green solvents for sustainable biotransformation. Third, the green solvents alternatives. There are multiple proven platforms, such as bio-based solvents, room temperature ionic liquids, deep-protected solvents, among others. Fourth, DSSs as future leaders. Firstly documented in 2008, DSSs have proven remarkable versatility with excellent selectivity and practical scalability across countless biotransformations. The field is really maturing. Fifth, the key advantage: environmental sustainability, economic cost effectiveness, regulatory compliance, and practical implementation in laboratory and industrial setting by combining enzymes with green solvents. And finally, the implementation path: clear, actionable steps for adoptions in both settings. So finally, the core message, and what I want you to remember. Biocatalysis in green solvents is no longer aspirational. It's not a future possibility or an academic curiosity. It is ready, proven, commercially viable, and implemented in manufacturing today. Thank you so much for your attention.